we've kind of looked at these voltaic cells, and we've looked at balancing these equations, and now we can use each of these tools to look at the relationship between the Ecell, or the standard Ecell of the reaction, and delta G naught. And we've kind of hinted at this, and we know that in a particular process, that if a process is spontaneous, delta G naught is going to be negative. We also said that the Ecell, or the standard cell potential, has to be positive. So what's the relationship between these? And when we look and we make a statement about these, we can say that work can be done when electrons are transferred through a wire. And the amount of work done, or the standard cell potential that we can get from that work that these electrons are doing, is, and we can say that this depends on the potential difference between the anode and cathode. And we're going to observe a thermodynamic driving force. That driving force comes when delta G naught is equal to a negative value. We say this is a spontaneous process. We also say that when the standard cell potential is positive, we get a spontaneous process. So these two have to be related. And when we set up this relationship, we can say that the delta G naught is going to be equal to negative N times F times E naught cell. In this case, N is the number of moles of electrons. And where this comes from in a particular balanced chemical reaction is that's the number of electrons that we cancel out on the reactants and the product side. So N is going to be a positive integer. It's going to be the number of moles of electrons. And I'll indicate here that this is always going to be positive. F is the Faraday constant, which is 96,486 coulombs per mole. This is named after Michael Faraday. So, and it's not the lost character, Michael Faraday. It's actually the scientist who derived this relationship, right? This value right here is always going to be positive. So, and I will note, and I have this later in the notes, that sometimes the Faraday constant will also be written at 96,500 coulombs per mole. If both of these are positive, the thing that dictates the sign is going to be the standard cell potential. So this is going to dictate the sign, which will indicate spontaneity. So it's the standard cell potential that's going to allow us to predict whether or not a reaction is spontaneous or if it's non-spontaneous. So from this data, we can look at an electrochemical reaction and calculate its delta G naught, or the standard Gibbs free energy. So let's calculate delta G naught in acidic solution for the following. Here we have Cr2O7 2 minus in aqueous solution plus solid iron, giving us chromium 3 plus in aqueous solution plus iron 2 plus in aqueous solution. So we need to break this down into our half reactions to determine what our cell potential is going to be. Then we can use the relationship that we just established to determine the standard Gibbs free energy for this particular reaction. Our oxidation half reaction is the easiest one to identify. In this case, we have solid iron becoming iron 2 plus, and this is going to be plus 2 electrons. The oxidation potential, or the potential for this half reaction, is going to be positive 0.44 volts. So the reduction potential for iron is a negative value, so here we have an oxidation half reaction. So this is going to be positive 0.44 volts for this reaction. The second reaction we have to look at, our reduction reaction, is going to be Cr2O7 2 minus, which is our dichromate, and that is going to break down into chromium 3 plus in aqueous solution. In this particular process, we need to balance out the waters. We need 7 waters over here on the right-hand side. And if we have 7 waters, we need to have 14 H plus over here as a reactant. Now we need to look at all the charges. On the left-hand side, we have a plus 12 charge. On the right-hand side, a plus 6. So that means we need 6 electrons over here as a reactant. The standard cell potential for this particular reaction is positive 1.33 volts. So in this particular case, we have 2 electrons being transferred in the first half reaction. We have 6 being transferred in the second half reaction. So we need to multiply everything in this first half reaction by 3. That allows us to have the electrons cancel. I'm going to put a little note here. This means that N is going to equal 6 for this particular reaction. When we put everything together and write the overall balanced equation for this particular process, we're going to have 3 iron solid plus 14 H plus in aqueous solution plus Cr2O7 2 minus in aqueous solution, giving us Fe2 plus in aqueous solution plus 2 Cr3 plus in aqueous solution plus 7 waters. Our overall cell potential for this reaction is going to be positive 1.77 volts. Yeah, there should be a 3 there. Thank you. So here's our overall reaction. And in order to calculate our delta G naught, we know that delta G naught is equal to minus NF times the E naught cell, which is going to be equal to minus 6 times 96,486 coulombs per mole. And I guess we should say that this is 6 moles of electrons that's being transferred. And then this is multiplied by positive 1.77 volts. Remember that a volt is in units of joules per coulomb. So our moles cancel out here, our coulombs cancel out, and we're left with joules. So our delta G naught is going to be equal to negative 1024.7 kilojoules. And this value right here is a pretty solid value, or a pretty large value for delta G naught. If you guys have been performing your thermochemistry problems, you should recognize that this is a pretty solid value. Okay? That's corresponding to a cell potential of positive 1.77 volts, which is also a really solid value.